Hello guys, I'm back. My name is Jeferson Costa. I'm a chemical process engineer with expertise in plant design, and today I will teach you how to add and configure a saturator in Aspen HYSYS. And this object is very important when you need to add to your process simulation a stream saturated with water and you have only the dry gas composition and also the temperature and the pressure. And moreover, I will discuss some points related to the control of the dew point in a process simulation. So enough talking, let's go to the screen. Just before I show you how to add and set the saturator to a process simulation in Aspen HYSYS, let me share with you the source of inspiration to this class. And it was a post from Karim Magdi. He did a process simulation and got a print screen from his process simulation related to the dew point control, and I was tagged by Jeferson to give some kind of comments to the Karim process simulation. In fact, I didn't any comments. What I added to the post of Karim was 3 questions, because I believe that is very important when you starting doing a process simulation that you understand what you are doing, and because without that you are not improving your chemical process engineering skills. So what I did was ask to Karim why dew point is controlling the process, because he did a dew point control process. How dew point is controlled in this process, where is the dew point controlled? And it is very simple questions related to the process simulation that he did. And he answered me, and I will talk a little bit about that later. But just to you take a look about the process simulation of him. Here you can see the overview of the dew point control system, and what we have here is a dry gas that is mixed with water to saturate this stream, and it passes through a heat exchanger. In fact, it is a LNG object in Aspen HYSYS to decrease temperature, and you have a 3-phase vessel separator, and the gas phase goes to the compressor where it is compressed to 1000 psi. The water goes from the bottom of the vessel separator and passes through a heat exchanger also, and goes to a strip column where the ethylene glycol is recovered and returned to the pipeline in order to prevent the freezing of the water content at the heat exchanger. And the hydrocarbon or heavy hydrocarbon is sent to a stabilizer where it is heated up with the air boiler, and the recovered gas phase returns to the process using a compressor, and the heavy molecules or the heavy hydrocarbons is withdrawn as stabilized liquid. And you can see that the source of refrigeration for decreasing the gas temperature is a closed loop. So we have here probably propane closed loop, where we have compression of the gas, we have cooling of the gas, and because of that we liquefy the stream, and with the expansion we reduce the temperature of this stream in order to have a cold stream, and with that have enough energy to exchange with the hot stream, and this is it. He shared some other pictures, so we have some pictures from the sale gas that is at the discharge of the compressor, although it is named with another designation. So my only tip for him, or my only recommendation to him, was to add a saturator instead of using a water stream, and he asked me why, and that's why I'm doing this video right now. So now let's go to the Aspen HYSYS and see how to add and configure a saturator, and why I did this kind of recommendation to him. And after that I will share with you the responses that he gave me and also some comments that I have about them. Here we have a replication of Carrin did, and I was not able to do that at the first site because the print screen of Carrin doesn't have enough information to do this kind, to do the configuration of the dry feed. So I asked him more information related to the process simulation, and he was very kind and shared this kind of information to me. And the information that he shared with me is available in these two PDF documents, ASW and also the dry feed workbook. So here you will find the conditions of the streams and also the composition that he used to do the process simulation. So these two files, it will be available in my Telegram channel in process, and if you want to get that, you just need to go there, and it is free for use and to get, no problem. The link is in the description of this video, or you can get the link in my website jeffersoncosta.com. From this flow sheet, I can identify which kind of information was added to his process simulation, because we have asterisks here, and these asterisks means that it was input added by the user. So I know that the dry gas, he fits, or he added the temperature, the pressure, and also the molar flow. And in the other hand, in the water stream, he added the mass flow and also the pressure. The others information was added by the Aspen HYSYS, and in the total feed, that is the mixing of the dry feed and water, he added also the temperature. He set the temperature there. With those information, I did the same, and you can see that verifying it where I have blue color, it means that it was added by the user. In this case, it was me. And where I have the black color, it means that it is a calculation from Aspen HYSYS. And what happens here is that although this stream seems to be saturated, and we will verify that with the saturator, what was my concern to Sahin is that if I change anything in the dry feed, as the mass flow for water is fixed, I don't have an update of the total feed. For instance, taking in consideration that the total feed is a saturated stream with water, if I change any process conditions in the dry feed, I should have a compensation in the total feed. What I mean, if I increase the dry feed temperature, I should have more content of water in the total feed. In the same way, if I decrease the pressure of the dry feed, I should have more content of water at the total feed. And it is this way because the saturation is a condition of equilibrium between pressure and temperature in the composition of the fluid. That's why it's better to have a saturated at your process simulation than specify content or a water content to your dry stream. So let's add the saturator, and the saturator is this symbol here. Up to this point, I defined only the connections. So you can see that the connections are defined. And I didn't add anything to the worksheet related to conditions or even to the composition of the components. And what I will do now is define the dry feed tool based on the dry feed existing. So it is the same process conditions, the same composition. So now you can see that my total stream is already defined, and the moisture or the water stream was already defined 100% water because it is a saturation with water, and the conditions was calculated or defined based on the dry gas conditions. And you can see that it is very similar to the one that Karim used in his process simulation. We have the same pressure, the same temperature. However, the molar flow and also the mass flow is not the same. And we'll verify that. So here we can see the comparison between the two streams or the two process, because they are different process right now. And in the first one, in the Karim, he specified the dry gas and also the water and also the total feed. And in my process simulation, once I did the saturator, I needed just to define the dry gas. And now let's verify, and as I told you before, if I increase the temperature of the dry gas, what I expected is that the amount of water also increases in the total gas. So let's suppose that I increase the temperature to 150 Fahrenheit, and you see that the total stream temperature corrected automatically, and also the molar flow increased. And let me increase just a little bit to you verify it again. Actually, we have 101, and when I change that, we increase it to 102.1. So in this case, any kind of modifications or updates that I do in my dry gas will reflect to my whole process simulation. On the other hand, if I do this in the Karim process simulation, what happens is that I need to do a new set of configurations. So I need to do a consistency check on that in order to get the conversion. But as the molar flow is already specified and it is fixed, it will not change in the total feed. And considering that we are dealing with a saturated stream, we cannot perform the process simulation this way, because if you are evaluating different pressure conditions and different temperature conditions to your saturated stream, it will lead to more water content. It will have an impact in the sizing of the heat exchanger, and it will have an impact in the sizing of the vessel separator. So it is very important to have the correct information in the correct place. And just another verification, as I told you, if I decrease the pressure of the dry gas, I expected to have more water content added to my total stream. So let's verify that. If I decrease only 50 psa, I increased the content of water in my total stream. So this is the way that you should proceed to do a process simulation with a saturated stream with water. But the class is not over. Let me return to the questions that I did to Karim to share with you some considerations related to the dew point control. The link to Karim post is available in the description of this video in YouTube. And if you want to add any comments, or if you want to have any kind of question to Karim, feel free to click on that. I'm pretty sure that he will do his best to answer you. So what we have here is a process where I get saturated gas, hydrocarbon, and I need to compress to deliver to my customer. And this gas has a requirement, and the requirement is in the description of the post. So the simple point control case for a produced gas at 15 Fahrenheit. So this is the requirement of the process simulation. But I asked him why dew point is controlling this process, and let's see the answers. The main purpose of dew point control for produced gas, sealed gas, is to ensure any hydrocarbon condensation, prevention during distribution and transportation, and for this process specifically, it's just a control test for that part of the simulation. Okay, it is partially correct. We have two kinds of dew points when we are talking about hydrocarbon gases or produced gas. We have the hydrocarbon dew point that will define the composition of heavy hydrocarbons that we will have in our gas, but we have also the water content dew point, and it is very important because depending on conditions of pressure and temperature, if we have a higher content of water, we will form hydrates in the pipelines, or during a depressurization we can have hydrates at the control valves or something like that. So it's not all important to have the dew point control in order to prevent the condensation of hydrocarbons in a pipeline, but much more important is to prevent the formation of hydration, and the cooling is one kind of control of water content at the gas stream. There are others like desiccants and etc. So it was very nice his answer, but it was not fully completed. So keep in mind that it is very important also to control the water dew point in the gas pipeline. The second question was how dew point is controlling the process, and his answer was dew point is controlled according to the determined requirement specs of the produced gas to be at 15 Fahrenheit at 1000 psi. That is not the answer that I expected. The dew point is controlled in this process based on the code closed loop. What I mean, to decrease the dew point of the gas stream, I need to cool down this stream in order to condensate the heavy hydrocarbons and also to condensate the water or the free water. And in this way, as I remove this heavy hydrocarbon and the free water, I will have a gas with a lower dew point. So how it is done is based on the temperature at the outlet of the heat exchanger. If my closed loop has any kind of trouble, for instance, I have efficiency in the compressor and my temperature in the closed loop, if it increases, I will increase also the outlet gas stream at the heat exchanger, and because of that I will have a higher dew point, and I need to fix the closed loop in order to get my dew point at the specification again. And the third question was, where is the dew point controlled? And his answer was the temperature of the gas stream out of the separator is the dew point of the final product gas, so he is the point of control. By trial, considering the critical datum point in the stream envelope to come near to the required spec. This was a very good answer, and thanks for your answer, Karim. And what he said is that the dew point is controlled at the outlet of the separator vessel. And it is true, once that we don't change the composition of the gas from the inlet to the outlet of the compressor, the dew point will keep the same. So if in this point here the gas complies with the requirement at the discharge of the compressor, it will require also, and take in mind that you always need to comply with the requirements of your process at the fence or the battery limit with your customer. Another information that I could add to the third question is that the requirements related to the dew point usually is defined by regulations. For instance, I have two examples to share with you. One is the specification for general purpose natural gas, and it is a draft from the Tanzania standards. So you can see that there is a table, a specification requirement for natural gas, and in this table there is the requirement for water dew point and at a specific pressure, and it is minus 15 Celsius degree. So this is the requirement in Tanzania, and I have also an example from a requirement in Brazil. And in Brazil you can see that the water dew point is minus 39 Celsius degree, depending on the region of the natural gas specification, and in the other regions is minus 49 Celsius degree. And of course there is some requirements related to the content or composition for methane, ethane, propane, etc. In Tanzania has also some specification related to contaminants and other specification. In the ASTM D1142, there is an equation where you can correlationate the Libra of water per million feet cubics of gaseous mixtures at pressure and temperature to the dew point temperature of the water. To finish this class, let me tell you that after many hours of research, I found the source of information that Karim used to build the process simulation. Here you will find the step-by-step to build the process simulation that I have shown to you. And this PDF will be available in my Telegram channel in process once we reach 100 likes in 7 days here in YouTube. And if you are already a member of my training program, it is available in the Dropbox of In-Process Booster. So this is it, my friend. I hope you like it. You can join my Telegram channel going to my website jeffersoncosta.com and click on Telegram. So there you will find the link to access my Telegram. And once we have 100 likes in these days, I will share the PDF file with all the instructions to build the process simulation. And you'll find also in my website the other links to my social media, like connecting with me in LinkedIn, and also the link for my YouTube, and also access to my blog, where I share much more content related to chemical process engineering and plant design. And I'll see you soon in the next video.